Hello everyone, my name is Przemek. Everyone calls me Rogue, as you have probably heard already. I'm security engineer at Red Hat, member of product security team, where I'm responsible for many shift left security initiatives and approaches at Red Hat. Next to me is Ralph. Ralph?
I'm Ralph. Everybody calls me Ralph. I'm architect of Conflux, which is Red Hat's build, test, and release pipeline for containers.
Today we'll present very shortly how the proactive security work plays a key role in trusted supply chain. At the beginning, let me just, there we go, it works. So we'll just quickly go through definitions, what exactly we need to build the trust. Then we will quickly define what are the key differences between proactive and reactive security work. Knowing this, I will show the security controls activities that are part of the Secure Software Development Lifecycle. I will show quickly high-level examples how we handle security controls in our Red Hat pipeline. Then Ralph will do amazing demo how we'll do it in reality. And after that, very quickly, we will show two real examples how we use what we do during the build time in our real work and how we can do proactive vulnerability management in reality. So let's start from the very beginning. What is necessary to build the trust? How you as a user, software user, can trust the software that you are using? Or in a different side, how you as a software producer can trust the software that you produced. So if we talk about building trust in software development, we need to identify two key areas, secure infrastructure and secure development. Infrastructure is the environment where you build your software. So you have to trust that environment. You have to make sure that it's designed based on POLP, principle of least privileges methodology, that you can trust this environment, make sure that the process built is not tempered and the outcome is exactly what you wanted. The secure development is another area related to the software itself, that the software, before it's released to customers or released to production, is checked, is verified. There is no important critical weaknesses, security issues, bugs, and of course, vulnerabilities. Today, we will focus on the secure development. In the industry, there are many standards and frameworks that can help you, guide you how to build trusted software. We have, for example, NIST Secure Software Development Framework, SSDF. We have OpenSSF Secure Supply Chain Consumption Framework. We have SLSA that covers the infrastructure portion. We have executive order requirements, DORA, CRA, and many more. Now let's take a look what exactly the proactive work is. So proactive security work is a set of all type of activities that you should do against your product, software product, before it's released to customers. Here we have malware detection before the build process is even started. You can test the whole source code that you are using for your build process. We have, during the build time, we have automatic security testing like SAS, DAST. We have also threat modeling. During the release, we want to make sure that we produce necessary attestation data, like we discussed already in different presentations, the SBOMs. So here we have all the work that can be done and should be done before product is released. The component that we built is released to customers. Why we do this? So yesterday, in the past, mostly we were focused on the quick vulnerability response. We want to just patch what was reported and release it and done. I'm done. And just waiting for the next vulnerability. That was the reactive part. Something was announced, I check my software, okay, I need to fix it. Now I need to quickly release the patch, done. That was yesterday. Today, if we take into account the software development complexity and our vision that we want to build and release new updates, software fast. And we've also take into account the number of vulnerabilities reported every single day. there is no other option like do a really big shift left and test the software, verify it, generate as much as possible metadata from the build time, and use this metadata to make sure that the software that is produced and released to end user is secure as much as it's possible. So this is what we do today. Why do we do this? Because we want to make sure that everyone understands very well that this is necessary to produce trusted, secure software, and it's not only security checkboxing that, okay, run it and done. We have to make sure that whatever we do during the build time, there is a big value and some outcome. For the future, automation. We have to, because today we produce a huge amount of data during the build time. We need good automation. Here is the space for AI where we can just quicker pass all this huge amount of data and take the right decision, what should be fixed, what can remain for the future. How do we handle secure development? Here in this slide, I'm presenting the high-level view of the secure development lifecycle and phases. And in every single phase, we trigger different security controls, security activities. It is very important to do the right things in the right place. So for example, during the design, we do threat modeling and security architecture review. During the build time, development time, like I already mentioned, we run different set of automated security testing, like SCA, scanners, SAS, DAS scanning. We produce build SBOM. During the release, we make sure that the content that we produce is meets our policy that defined by Red Hat. We have to make sure that it's signed correctly, it's distributed in the right way through official Red Hat distribution channels, and we also produce, for example, release SBOM. So this is how we handle it. Now let's take a look how it's done in Red Hat supply chain. So here is a diagram where we see how the upstream code goes to Red Hat pipeline, where we directly in the pipeline itself, we scan it, test it, generate necessary attestation data. At the end, we sign it, the content, and deliver it secretly to our customers, and everything is done in our pipeline. It's very important to make sure that all the proactive security work is key part of the build and release pipeline, that the security is built in the software supply chain. It's not a side process handled completely independently. Let's take a look a little bit closer to our Red Hat build pipeline. So maybe you already attended previous presentation about Conflux, but today let me quickly repeat. Today we are working very actively on the new solution called Conflux, which is an open source, comprehensive, robust build, test, and released factory based on Tekton and built around software supply chain security from the very beginning. In Conflux, we build, run various tests, and at the end, we verify results of this test to make sure that the content that we release at the end of the process meets our security standards. Conflux, by default, generate all necessary artifacts to meet the SLSA build level 3 requirements. Here is a very high-level view on the Conflux pipeline. As you can see, every single task is executed in a very controlled way. For that, we use Tekton chains, and every task produces necessary attestation data and provenance, and that at the end, we review that data in a Conforma project to make sure that particular final build meets predefined Red Hat build and release policy. Now, let's quickly take a look at two examples, and then I will allow Ralph to show the presentation, real presentation. So here we have a build with associated attestation data. So we have, provenance information from metadata from every single Tekton task. So as you can see here, this particular build cannot be released to production. Why? Because the base image that was used to build this component is not from the allowed image registry predefined by our rules. So this build cannot be released to the production. Here we are having another build, another set of associated metadata with this particular build. Here, everything is correct. Our predefined policy rules are met. As you can see, the CVE scan has an alert, but this one is not a blocking rule. That's why still this particular build can be released to production to customers. And now, Ralph, stage is yours.
Well, I'll show. I'm going to drop out of presentation and switch over to a terminal. I've got here a repository. Is that readable? Yeah? In the front it says yes. In the back, no? I can try. It'll mess up the formatting a little bit, but no, I can't go any bigger than that. Is that okay? Okay. Oh, and I've got some feedback. I'm good. Okay. The URL at the top is meant to be something that you can follow. GitHub.com, ralphbean/example. If you want to follow this afterwards and try to go through the steps, you can. Through the demo, I've got 3 different components that have been built in Conflux. We're going to look at them and see what their logs look like. They have different, I guess, aspects to them that are going to result in different supply chain properties that we'll see. We'll step through them in detail in a minute. In addition to those 3 components, we've got 4 different policies here that we've created. So like when we use Conforma in Conflux in a production environment, we have different kinds of targets that have different expectations, a production environment or a stage environment, an SRE environment or a dev environment, and we actively place different policies over those endpoints because we want to encourage innovation where we can, but we want to encourage restrictive builds, compliant builds where it's absolutely necessary. So here I've got 4. Can you kill your mic? Oh, it's better now. It's better now? It's better now. Okay. The 4, no, it's not. There's a little, there's a button on top. If you flick it to off, see that one? Does that work? Okay, cool. There's 4 different policies here. The first one is, no, it's happening again. Oh.
I think it's your laptop. Because his mic is doing the same thing as your laptop.
Okay. I'm going to stay back here. 4 different policies. The first is the simplest, requiring only SLSA build level 3, which for Conflux is simple. You almost can't get a build that's not SLSA level 3. The second, policy B, is a little bit more restrictive. It takes the same requirements as policy A, SLSA level 3, but it's going to add some CVE blocking requirements. If in the provenance of the build it can find record of a CVE scan, well, first, if it can't find record of a CVE scan, it'll fail the build. If it does find such a record and there's CVEs present that meet some sort of criteria in that policy, then something will fail policy B. Policy C is built on top of policy B, looks just like it, except it adds the requirement that the build is a hermetic build, which I'll explain more when we get to, and that the content that's going into the build only comes from certain curated sources. And finally, policy D is just like policy C, except it's weakened a little bit in order to allow for content coming from a particular source. Let's say we have a business need, or we have a good business reason to allow content from this source. You can do it with an explicit exception for one particular set of content, one particular destination. Here, this is more for the record later, how to use this repo. If you follow it through, I have set up Conflux locally in an instance of Kind. Kind is Kubernetes in Docker, so you can run a Kubernetes cluster locally. If you copy this, it's got my username in a bunch of places, so you'll need to replace my username with your GitHub username if you fork it. And then you simply apply the resources in this directory to your local Conflux instance, and it'll register those 3 components from the beginning and those 4 policies in the cluster so you can replicate the set of builds. By registering components 1, 2, and 3 with the cluster, it's going to, with your local instance of Conflux, it's going to instruct Conflux to start monitoring your fork, that GitHub repository, and install a webhook such that every time you push new commits to that fork of yours, it's going to fire and connect to the local Conflux instance and kick off builds to see how it goes. Finally, there's a UI that comes with Conflux, which we'll click to and see here. My local instance is running here. And so this is Conflux. You can see, well, I'll step back up a level. There's multiple. It's based on Kubernetes in the first place, so you get the properties of namespaces that you'd expect with Kubernetes. Here I've got one namespace for me and one for Rogue. There's this example app that I've set up based on the repo I was just showing. And we can see here the components. Components 1, 2, and 3 are registered with the system, and we can see the last commit that was built for each of them. If we click into this activity tab, we can see the history of commits across components that are registered with this app. And we see the most recent one here. This is last night. I couldn't get the demo working. I needed to increase timeouts for really slow conference Wi-Fi, so that made this work. I'm going to zoom in just a touch so you can see better. Here we have from that one commit triggering 3 different builds, and then each of those 3 different builds was subjected to review under those 4 policies. And we can see that component 1 passed policy A but failed all the others. Component 2 passed the first 2 policies but failed the last 2. And then finally that last component failed that policy C, but it passed that policy D. Yeah? If we click and look into one of these particular builds, we can go to the pipeline that ran for it, but my formatting is weird because of Zoom. Scroll down. This is like what Rogue showed on his slide, but slightly enhanced. That screenshot was taken from some time ago, and we've added new SDLC checks to the pipeline since then. But you can see there's some expected stuff at the beginning, cloning the Git repository and building the container. Before it is this prefetch dependencies step, which is an important part of the way we do hermetic builds. But maybe I'll talk more about that later, see if we have time. And then finally, at the end, after you get the build of the image completed, you have all of these SDLC checks that run associated with it. If you can see, there's a CLAM AV scan here for doing malware detection, multiple SAST checks, performing static analysis checks on the source repository that the image is built from, a deprecated base image check that's looking for end-of-life information about base images that are contributing to the image build, and so on. Right? So, all of this information, this entire chain of events, is what's recorded in the provenance. So the provenance for us is an important part of the way the whole system works. That Conforma engine takes as its input only the provenance record that's generated by the build system, cryptographically signed, and then pushed into the container registry, which has fun properties, right? Like, so you can build on one complex cluster, get a signed attestation about the whole record, and then end up releasing it from a different complex cluster as long as that cluster trusts the key, the build time key of that other cluster, because there's no, like, dependent programmatic interfaces between the two other than what's in the OCI registry, which is nice for us for a disaster recovery point of view and flexibility and reliability of the system. I'll switch back to here in my notes, component 1. So this demonstrates a basic build. Like I was saying, it's a simple build that installs only some Python packages. Let's look at it. Component 1, container file. It's not an exciting container file. It's building from a base image. And note, I've put in the comment here, I lost my audio. Can you still hear me? I'll keep going. We're going to lose it on the recording, but that's okay. Okay. This is a component 1, so it's built on a base image that I've deliberately pinned to an old base image so that the image has CVEs in it. The latest version of this base image that's come out has those CVEs fixed, but I wanted it to fail policy B, so I pinned it to an older version. And all it's doing is doing pip install here on some requirements. Because this isn't a you're laughing. What's going on? Oh, thank you. As you can see, and that's what this build looks like. What we saw when we looked through the UI, right? If we compare what we're seeing here in Conflux against the OpenSSF Secure Supply Chain Consumption Framework S2C2F. Man, that's a hard one to say. Yes, I had to practice saying it. Some requirements here about we need to be scanning OSS for known vulnerabilities, which of course we are. We're running Claire against the image to look for known vulnerabilities, surfacing those in the UI to make them available to the developer. And finally, a thing that I haven't demoed here but is an important part of Conflux is that we are running an instance of Renovate bot associated with the cluster. So this is not part of the CI/CD process, but really it's a feedback process on the Git repository. If you know Dependabot is, if you're on GitHub, everybody's on GitHub. Dependabot is, what am I trying to say, by far and away the de facto leader in that kind of tool for updating dependencies. Renovate is an open source clone of Dependabot, and so with Conflux we're running an instance of Renovate to drive that vulnerability remediation back into the Git repository of projects. So that's it, I think, on component 1. Can we look at component 2? Component 2 is different. It demonstrates a build where something bad has happened. It has in its Docker file this line, run curling some shell script from some place. Where's Brett? Is Brett in the room?
escape.
Oh, he escaped. He loves curling shell scripts and running
Yes.
them in shell, right? This is what, but my friend Remy calls them the curl pipers. So this is what this script has done. And so if we take a look at this command, here I'll go run it myself. Switch to another terminal, exit out, and I run this. Oh, it's an innocent script. It just echoes hello world. That's great. We can totally include that in our image, right? But if we go here back in the Complex UI and we look for our list of pipeline runs, and the latest commits, build 2, and we look in our build container logs, we see that we ran that step to curl cdn.3d.org/install.sh. We made it executable and we ran it, but it didn't print out hello world. Oh no, it printed out hacked. What happened? Yes?
In reality, I don't think that's a security issue because who's inspecting every command that runs on their computer? Nobody. And really, if you're downloading software from that website, you're actually trusting the people of that website. So if you're going to install it, yeah, that's a pipeliner, but if you're going to install like a 2000 shell script, 2009 shell script or Secure or whatever, you essentially need to trust the authors of that. If they're going to play with you with like that, you shouldn't be trusting them in the first place. So even if you download it, read the script, they might put some backdoor that you will never read it.
Right, that's a fair comment. He was handing you the mic, but should I repeat it? That there's some difficulty in trying to audit the source of something from a third-party site you want to review. It's a difficult thing to do, and if somebody was going to be untrustworthy like this, then you shouldn't be depending on them in the first place. Yeah, I think that's a fair criticism. I want to highlight that like de facto tools for analyzing the manifest of an image and reporting for, and this is like kind of back to the thread of our talk, vulnerability management. At scale, if you have lots and lots of components across lots of teams that have lots of dependencies, you need to have programmatic access to the sources of everything that went into a build. And if you run static analysis tools like SIFT or related ones on the image, you're not going to find a record of install.sh or anything about this site that came down into the build. So in this case, what has happened, well, I'll show in component 3. Let me scan my notes and see, is there anything else I want to talk about? Because in component 3, I want to show how this is dealt with in Complex with a hermetic build, which gives you a different outcome. Yeah? If you run SIFT, I've already said it, I guess I don't need to demonstrate it. If you pull the image and run SIFT against it, no record of that, and again, showing that that's the content of the build. So, and end of component 2. Just for fun. The script that served this was a Python, a Flask application that's looking at the headers of the request, and it's a motivated attacker, let's say, who knows the version of curl that's going to be live in the build system, and so only wants to serve the hacked version when that's requested, but will serve a happy hello world version to anybody else who checks, the developer who's confirming locally. In component 3, we've got a hermetic build, and in order to do a hermetic build in Complex, you have to pre-declare all of your dependencies up front. And that step in the build pipeline I showed that has the prefetch dependencies that runs before the build is going to act on those declared dependencies, pull them down, and then make them available to the build over the file system. The build will run with no network access to the internet. But this gives us a way to be sure about everything that's made its way into the build down to the digest. And it requires let's see, let's look in component 3, artifacts.lock. Is a file that is respected by that prefetch dependency step that will take particular content that you want to pull down and requires that you've supplied a digest to match it. So in this case, if it is a 5,000-line shell script, it's hard for a developer to review that. But in this case, if the developers pulled it down and verified it, they must supply a digest to the build system in order for it to run. In this case, component 3 ran without failure, right? You would expect that if that script is serving the hacked version of the script, the developer has computed one digest, this SHA-256-209 CD, and then when it goes into the build system that it would fail because the digests don't match, right? A hacked version is served. But it just so happens that the version of curl that's running in the prefetch step is a different version of curl from the one in the build, and so the Complex build is actually served with the correct version and the build succeeds, but you can see how it would go one way or another. If you look in the SBOM of this image as well, let me see, I have notes on how to do that. If you look in the SBOM of the image for component 3, you do see a record of install.sh coming down, just again, because we've declared it explicitly. To compare here is some about what's going on with component 3 against other properties in the S2C2F framework. In terms of auditability, the hermetic builds, I already kind of discussed it, ensure that dependencies are exposed in the manifest for audit and control. We can prohibit the use of unauthorized sources. So for instance, the developer has gone off and decided, oh, this install.sh script is totally what I need, and as long as I declare it as a hermetic build, it'll be fine, I can get it in and it can ship. But if we're using policy C to control our egress into some production environment, then that's going to be blocked, right? Because Conforma is only allowing content from certain sources. Let's take a look at those policies really quick. If I look in common, policies, policy D, make it a little bit smaller. There's a lot of boilerplate at the top in terms of what this resource is. It's an enterprise contract, Conforma policy, description of what it does, and so on. But down at the bottom is what's important. This policy is defined by this set of included rules that are coming from data sources declared in the data block. This @ symbol is for a collection, so the collection of rules that together taken can verify that something is SLSA 3 is represented by that line. The CVE blockers rule that was added in policy 2 is here. But the hermetic build requirement is here, and the SPDX SBOM allowed package sources rule is the thing that restricts anything found in the SBOM must conform to a set of sources that are explicitly allowed that come from the data rules associated with this. But here, we've allowed for this policy, making policy D different from policy C, a special exception to say we're going to allow for this particular destination, this particular package source. Let's say that we reviewed it and we decide it's okay. That's how you achieve that with the machinery. So Conforma prohibiting the use of unauthorized sources covered it. Looking at ingesting content from S2C2F, Conforma policy gives us control at release time over what kinds of open source components are ingested. And finally, there's this bit in the S2C2F about mirroring a copy of all OSS sources to an internal location. What's going on in the conflux pipeline across the board, we have a pattern that we call trusted artifacts, where between all those steps in the build pipeline, there's no persistent volume claim that's available to them. They all have only their own local disk. And so anytime one of them performs some action and produces some new result, it has to push that artifact back up into the OCI registry and emit the digest of the thing that it just pushed. Subsequent tasks pull that down from the OCI registry and verify the digest before moving on. And this is how we ensure that there's no sort of tampering going on in between. If you have a persistent volume claim, we can never really be sure that some other task wasn't running contemporaneously, mounting it and meddling with whatever was supposed to be in between. So but as a side effect of that, we get the solution here to ingest 4, the last requirement on the list, to mirror all copies of open source source code, which everything that came into that prefetch dependencies task is pushed back into the registry, associated with the build, and follows the build along in its life cycle, giving us a full set of sources, which we can then audit later, rebuild if we need to patch something ahead of upstream, but also enables us to do GPL compliance, right? Because we have all the sources for every build moving along with the build, which we then distribute down the line as a source container. Cool. These are commands I won't switch over and run, but are really cool. If you've never tried the cosine tree command, I find it the most useful, like, introduction to the beginning. If you're just learning about attestations and this whole kind of stack, the secure supply chain stack, cosine tree will look at a particular artifact. Here, this Quay.io experiment Ralph Bean component 3 in this tag. That's one of the builds that came out of component 3. You can inspect it with cosine tree to find the associated and related supply chain security artifacts. Is it microphone time? It is.
I think that's just dying. Okay.
It's on? Okay, cool. Thank you. And then lastly, we're unfortunately in the middle of a little bit of a transition where the artifacts that you find via cosine tree are located via a tagging convention that cosine and the SIGSTOR community invented, but they're moving away from that to OCI Referrers API, which the OCI 1.1 distribution spec defines a way to upload artifacts that refer to another artifact. And that's where everything is headed. You can see that our own system is kind of split between those right now. I'm using the ORAS command, ORAS discover, to find related OCI artifacts. Cosine tree doesn't know how to do that yet, and ORAS doesn't know how to do the first one. So unfortunately, we're in the middle, but I expect we'll eventually entirely be on OCI artifacts, OCI Referrers API artifacts soon. And I'll skip this one. This is how to retrieve all the sources from Quay, but we'll move off that. And actually, I'm going to ditch the microphone. I'm done. How do I turn it off?
Is this one still working? I think that, okay, this one is still working, cool.
I have some questions about this cryptography signature and all of that. Should I ask now or maybe later?
Maybe we have 10 minutes, so let me just finish.
Good idea.
Slideshow? There we go. Okay, so thanks, Ralph, for the great presentation. We quickly just went through how Conflux work, how we produce attestation data. You have seen already the CV scan blocking rule and also the SAST Tecton task that was executed, and we collected all provenance data from that Tecton task. So now let's focus for a moment on that secure development and those two tasks. So first, CVE scan task and proactive vulnerability management. So we believe that reactive part that was done in the past so far and proactive work can work together and supplement each other. How it can be done? Here on this diagram, we have the left side, which is the build time. On the right side is that what was already released, what was already recognized as a vulnerable thing to some new reported vulnerabilities. And as you can see, during the build time, we scan our build, like Ralph was presenting. We detected some CVE. Then, based on our defined rules, we can define that, okay, this particular build contains this CVE. It's not that very important thing for this build and this particular product. So that's why we can still release this build to production to make it public. But at the same time, we have to immediately update our security metadata, CSAP VEX files, to make sure that immediately when the component is in production, customers, users can use our security metadata to make sure that this is the situation, security posture for this particular component. At the same time, the already public data that was already reviewed by Red Hat product security team, and we have our own risk assessment for our products. These data are used during the build scan. So we can make sure that we are not using upstream data and where we generate huge amount of false positive, we use our already created data. So those two approaches works together. This is the high-level vision of the pipeline. This is what Rafa was presenting. We have that git clone prefetch step. We have the build time. As an outcome, we have SBOM and image. We scan then SBOM or image, depending on our use case. As an outcome, we have the CVE report. And CVE report is then analyzed. And based on the conformal rules, based on the scan results, we can define if this particular build can be released or not, or maybe some other actions are necessary. What are the benefits? So we have the very early warning about not address CVEs in the build time. Owner of the component can address it during the build time, not afterwards when it's already released. What is also very important, we have an option to detect all type of emerging security data inconsistencies in our CVE VEX files. So for example, in case of CVE was missed, in case of wrong risk assessment, all those types of use cases can be addressed. SCA scanners many times, because they use reverse engineering, generate a lot of false positives. If we can detect this type of discrepancies, problems in our data during the build time, we can in advance update our public data. So when the product is already released, scanning vendors, even if they use reverse engineering, still we can give them right, accurate information that this particular component, yes, we know if you do reverse engineering, you can claim that it's vulnerable, but it's not. If we publish this data, no problems. How about avoiding vulnerabilities in the first place? Here we have our SAST task, where we generate huge amount of data. And as a maybe example, in Red Hat Enterprise Linux 10, we have 2,100 RPM packages. When we scan them by our SAST tools, it was 86,000 of identified security issues. More than 80% false positive. So SAST scanning is good, but it's time consuming, and trying to process this is not efficient. No one is able to fix everything what is reported there. So how we can improve it. Our POC was to take scan results and enrich it by using weakness data associated with our CVE records. So for the exactly same product, the same component, we have a list of historical CVE records and associated the root cause of that vulnerability, the weakness that caused this particular issue. Combining them together, we're able to find patterns and improve the weakness remediation suggestions to our engineering folks. By this, engineering teams can focus on the right things, address them, reduce the number of CVEs reported once the product is released, and of course, at the end, we will improve customer satisfaction. How exactly it works? So here in this slide is a high-level diagram that shows on top data what was already released. What was released was vulnerable to new vulnerability reported, and we go through the risk assessment process, we publish data, we patch it, and we store the record of this product. This component was vulnerable to this CVE, and associated weakness is this one. On bottom, we have scan results. SAS scan results from the build time for exactly the same component that we're just building new versions of this component, combining this huge amount of data together. And for that, we need AI support because no one is able to parse this amount of data manually. We were able to identify most precisely the weakness categories that are much more important and should be addressed by the owner of the component. So we just give them much better weakness prioritization information. Still I have some couple of minutes. So here's a real example. On the left side, CWE data from CVE records for one product and one component. On the right side, SAS results for exactly the same product, the same component. I highlighted patterns that were on both sides. Using AI, like I mentioned, we can combine this huge amount of data. I was presenting in the previous slide only some very, very short screenshot from the whole huge amount of data. We're able to provide quick information to the owner. Hey, you should focus on those three categories, weakness categories. First, data neutralization problem, memory buffer issue. Second one, authorization problem is the third issue that should be addressed. So that's it. It was very fast. Questions?
About the build process, the author of the software issues a new release, and then the build machine creates the build artifacts, and then signs it cryptographically from the same machine, and then that's uploaded, right?
Can you repeat it?
Yeah. So when a new release is made, the author of the software makes the release, or the maintainer, whoever, and then that gets pulled in the build machines. The build machines build the artifacts and then sign them cryptographically and then push them to some repository.
That's essentially right, but I think at the beginning the most common pattern is to be building off of main or off of some sort of release branch, so that it's 2 minutes. So but it's not necessarily like a release that you would see to like a GitHub releases API and then moving from there, but it's more of a continuous delivery orientation.
That's the pattern. So I see that I need to trust two things, like the author of the source code and the build machines, because if the build machines are compromised, everything is fucked up.
Yeah, absolutely.
So I'm a project maintainer, also upstream project maintainer, and what I did is I want people to only need to trust me, know the build machines. So what if I do a build in my own laptop, sign it cryptographically with my key, and the build must be reproducible. So then a build system builds the same thing from the source code, unrelated to my signature, and then my signature should be able to verify that build. So you don't need to trust the build system and the build machine because the signature was done on my laptop.
Totally. This is like the Debian reproducible build model.
Yeah.
It's a great idea. In the SLSA build conversations, they haven't included reproducible builds yet, but it's under debate for whether it should become build level 4. And part of the problem is like proving that for builds on a build-by-build basis, because it just becomes expensive to build multiple times in practice. But of course, Debian does and tries to do that. It becomes a little bit weird because one of those two builds is built and signed by you, and that is not like, the signing key material was like available to the build process. But then, of course, you get the assurance that it's built somewhere else. So
no, because the key is not available during the build. I only introduce my key in the laptop when I sign, which is after the build. But
sure,
yeah,
the attestation can't know that, or maybe it can.
Yeah.
We can devise a way for it to know that, but not immediately.
so that thing is, you only need to trust me as a developer, which you already need because I wrote the software.
Yeah.
So you reduce the problem of the build machines.
No, it's a good idea. It is.
Only if I exactly build it in the same way how you did it. If I
Yeah.
take your source code and build it in my own way, then I just need your source code. I don't need to trust your build.
But if you're changing, like if you're a downstream that you apply changes, then I want to trust you, then you should sign that in your own laptop and then send that to your build machines to build the same exact thing. And your key should still verify that. So I want to trust you, not your build machines.
Yeah.
Mm-hmm.
We've got the X on time. Munawar, for a last question, I'm going to do it.
Sure. So I want to understand the SAS versus SCA and the data, how they're being matched. I didn't fully. So SCA tools, they give you known information like past vulnerabilities, and then you map to the corresponding CWEs. The SAS scan gives you new vulnerabilities, like these are the new ones. How is the matching done then? Like, is it such that you are just relying on historical data, like this build was historically vulnerable to this, and therefore this new SAS scan should be prioritized? But in that same logic, like Log4Shell would never be, like if some tool was able to find Log4Shell, which by the way our tool did, but anyway, that's a separate thing. You are not able to prioritize that because there was no LDAP injection in the past by any SCA data.
So based on our this is a great question, thank you. Based on our observation, over the years, people, instead of addressing the root cause of the problem, they always were focused, okay, let's just release the patch and done. That's why Log4j, how many times Log4j was patched? They reported 4 times.
4,
yes. Yeah. And only the last time it was, in theory, addressed finally. So SAS scanning gives you a set of weaknesses, not vulnerabilities, weaknesses based on analyzing only the source code, and that's it. Knowing also information for the exact, this is important, exactly the same product and the same component from the historical CV records and associated weaknesses to those records. Taking weaknesses and weaknesses reported by SAS scanning, now I can combine them together to make sure that I can find weakness patterns. This is the logic. We are having the speakers of how is it called? Speakers office hours right now, so we can just go there and discuss it in the details.
Thank you.
Thank you.